All right, good morning, everybody. So, we're picking up the journey that we're going on. And last time we talked about how to write tensor equations in arbitrary coordinates and how to. Oh, there's that. Huh. Now we're right back. Okay. The machine, I guess, really didn't want us to start before 9. Uh, So today what we're going to do is take that mathematics that we've been developing and we're going to construct the Einstein equation, which is what tells us the part that Wheeler described as uh, matter tells space-time how to curve. And so we're going to try and build that equation. So here is an outline of what I hope to do today. Going to talk about the stress energy tensor, which is the tensor way of expressing the source of the gravitational field. Then we'll talk about the Riemann tensor, which is the tensor that describes the curvature of space-time. And then we'll do the actual building of Einstein's equation. What kinds of considerations do you have to go through to make one side, uh, the curvature side, connect with the mass energy side? And then we'll talk about some more interesting theoretical issues, which is a different way of thinking about the Einstein equation from the way Einstein himself did, a more modern way of looking at that. And then we'll try and deal with the troublesome question about whether gravitational fields have energy. So those are the goals for today. So our basic task is to try and find a generalization, a tensor generalization of the Newtonian Poisson equation, which looks like that, where this is the gravitational potential, this is mass density, and we're going to try and generalize that in a tensor way. And if you printed out my lecture number 1 and looked at the electricity and magnetism part that we didn't really get to, then you'll see that what we're going to do is sort of the same thing that we did there. And one of the first steps is to try and decide what kind of a quantity this is, what kind of a tensor quantity it is. And so we first have to ask, is it a mass density or is it an energy density? And then how does the density transform as you go to different reference frames? That'll tell us what kind of a tensor quantity we're looking for. Is this a relativistic scalar? Is it, as it was in electricity and magnetism, the charge density turned out to be the time component of a 4 vector? What is this? That's what we have to decide. So first of all, let's deal with that first question. Here is a simple argument that tells you that rho ought to be energy density, not mass density. And that would be really hard to tell in Newtonian mechanics because nothing in sort of the Newtonian world moves fast enough that there's really any distinction between rest mass density and energy density of normal objects. Even the sun there's not much difference there. So we really have to think about this theoretically. But I want you to imagine a mirrored box that contains a electron and a positron, and they're bouncing around the box, and they have because the electron and positron have mass, rest mass, there will be a rest mass density. It will create a gravitational field, and you'll have a distant particle be attracted to that gravitational field and start falling towards the box. All right? Now let's imagine that just as this distant particle is nearing the box, the electron and positron find themselves together and annihilate each other. And now you've got two photons in the box which have no mass at all. Okay, so my mass in the box has gone from something non-zero to something zero. And now whatever the distant particle was, there's no gravitational field anymore. If mass were the source of the gravitational field, there would be no gravitational field anymore, and my particle would go back out to infinity with kinetic energy that didn't come from anywhere. So if it's not, the basic problem is that mass is not conserved in physical processes, whereas energy is conserved. So if energy is the source of the gravitational field, then there's no difference in the gravitational field created by the box if the energy is in the form of an electron-positron pair or if it's in the form of two photons. It's still the same amount of energy, still the same amount of energy density. So the gravitational field of such a thing would be invariant. You don't get violations of energy conservation. Does that make sense? So that's a kind of a thought experiment to say that you will avoid being able to violate conservation of energy as long as the source of the gravitational field is energy. Okay? So then how does energy density transform? Well, we have to think about, it helps to think about a certain kind of fluid. We're going to take a really simple kind of fluid to think about this initially, called dust. And dust is a kind of a fluid where the particles in a given neighborhood all have roughly the same velocity. And the idea is sort of like the household dust that you see in a shaft of sunlight that's sort of moving along with the air currents, and then in a neighboring, in a small region, all the particles move along with the air current together. So that's the vision. It's not the kind of stuff that you find under your bed. Okay, so we're going to consider a tiny box containing a certain countable number of dust particles, and it has a volume v sub 0 in a locally inertial reference frame. In whatever locally inertial reference frame, the dust particles are at rest. So you imagine a frame moving along with the dust particles so that they're at rest in that frame, and in that frame the box has a volume this. So the number density in that inertial reference frame is just n over VO. So then you think about looking at this in a different inertial reference frame where the box is moving with a certain kind of speed. Then the box will be Lorentz contracted, and so its volume is a little bit smaller in the new reference frame than it was in the original reference frame. So the new number density, still the same number of particles in the box, but now the density is a little larger by a factor of 1 over the square root of 1 minus v squared. Okay, so that tells you something about the transformation. So that in that second locally inertial reference frame, we can write the 4 velocity of the dust particles in the region that we're talking about this way. This is the standard 4 velocity in a Lorentz flat space-time background. And we could write that as the time component. This is the time component. We could write all the other components in terms of their ordinary velocities times the time component. And so we could write the number density, which is n over v, which we decided was n over VO times this Lorentz contraction factor. We could just write that as the original number density times the time component of the Four velocity of the dust. And then we could write the density, the energy density, is the number density times the energy of each particle. And each particle's energy is the mass times its Four velocity time component. And so this is the expression for what the density is in that frame. So what kind of a beast is that? Yeah. So this is a relativistic scalar. The energy density in the dust particle's own reference frame is a relativistic scalar because everybody can agree what reference frame that is, and they can all look as you count up the particles and measure their masses and energies in that frame. And then to get another frame, you just take two time components of Four velocity. So if you're going to write that as a general tensor quantity, what kind of a quantity would it be? Yeah, it's a second rank tensor, and so the general expression would be, here's the second rank tensor, this is the full tensor quantity. So it's basically, you have to get the second rank tensor behavior, transformation behavior, because you get sort of one factor of contraction from the Lorentz contraction, but then the energy itself transforms as you go from frame to frame. So you sort of get two powers of gamma, which you can't get by transforming a Four vector. You can only get that by transforming a tensor. So this is the stress energy tensor for dust. And there are two ways that you can look at the other components of this. So the time component is the energy density that we expect to be the source of gravitational field. But of course, if this is really going to be the source of the gravitational field, then there are going to be other components that come into this for relativistic fluids. So let's think about interpreting the other components. So if I'm looking at the Tx component, that's what this is going to be for dust. And so here's the mass, the number density times the mass. So that's the mass density in the frame. And then I've got this factor of ut and u super x, which I could think of. This is density and the times. So this is number density basically in the new frame times the x momentum of the particle. And so if you multiply those two things together, you get basically x momentum density. In other words, the density of x momentum of the particle. And similarly for Ty and Tz. On the other hand, we could regroup the terms that we've got here and connect them in a different way and say this is still the number density, and then I've got I could have written this instead of u super x, I could write it as u super t times vx, and then group these two terms together. That's energy. So this is this is the energy of the particle. This is the number density of the particles. So I have So this becomes energy density times Vx, and I could think about that as the amount of energy that per unit area, per unit time that's flowing through a surface. So I could also think of that same component as energy flux in the x direction. So either way, I can consider it the density of x momentum, or I can consider it as energy flux in the x direction. So what do you think T super xy would be? Yeah, yeah. And so instead of this is Tx, so this would be energy flux in the x direction. If I'm thinking xy, it would be x momentum flowing in the y direction. And if I had xx, it would be x momentum flowing in the x direction. And so on. So these that's the way to interpret these. Yes, question. Mm-hmm. Mm-hmm. That's right. So the density could vary, the four velocity could vary. So this, in general, this tensor is going to be a function of position. Okay, and you could think about that. For example, a rotating star, you might have your density be roughly constant. You might for a simple model, but in real stars, the density is going to vary with radius. And then the four velocity is also going to vary. It's going to be the greatest at the equator. It'll be small near the pole or on the central axis, and so on. So in real objects, this will be a function of position. Does that make sense? Other questions? Yeah. Okay. So anyway, that's the way to interpret this. So of course, real fluids are not like dust. Real fluids have random velocities. And so if you take a small region, you can't say all the particles are moving together. They're moving about randomly. But what you can do is build that up by treating the subdividing all your particles into classes, subclasses where all the particles are moving together. So you say, in this region, how many of you are moving in the plus x direction with this velocity? And people raise their hand, and you collect all of those people into a class, and you say, okay, this is dust for that particular velocity in that particular direction. And you add them all together, and in the frame where the bulk movement of the fluid is at rest, then and the particles are moving around randomly. If you think about it, if you think about classes of particles that in common are all moving in the have a certain x component of velocity. If they're moving randomly, they'll have y components of velocity ranging from minus infinity to plus infinity, even though they all share the same x velocity. And so if you add all up the dust classes, they're all going to cancel out. And the only ones that aren't going to cancel out is the time component. That'll always add. And then xx and yy and zz, because you'll get squareds. You'll get Vx squared instead of Vx times Vy, and that will integrate to 0, but Vx squared won't integrate to 0. So when you add them all up, you get something like this, and you can write this in tensor form like that. Again, these are scalars. They're the density of energy and the pressure evaluated in the frame where the fluid is at rest, and then you multiply by the bulk velocity of the fluid, and this is still a tensor correction term, but it leads to this form as this calculation down here suggests, if you're in a locally inertial frame where the fluid is at rest, which is what you want. So this is a general tensor expression for fluid where the velocities are random. And this is still not a really realistic model of a fluid, but it's not too bad. And in fact, for most astrophysical sources of gravity, you could even use dust, the dust model, because the dust model would have zeros here in the frame where it's at rest, but those pressures are actually really, really close to zero for almost any object in the units we're looking at. And I'll have a little exercise to show that. But basically, this is a good enough model. It's even more than we need for most astrophysical applications. All right? So, I want to talk briefly also about conservation of energy and momentum. It's expressed by this formula, which at the origin of a locally inertial frame reduces to just that simple divergence of that stress energy tensor. And because in a locally inertial frame, what does the tensor derivative become? It just becomes the ordinary derivative because the Christoffel symbols are all zero. Okay? And so I'm claiming that this expresses energy conservation. Why would I make such a claim? Well, if you think about, you can think about each term in this expression. Think about energy flowing through a tiny box along the x direction. So this is the flux of energy, according to what we decided. So this is, let me take the energy that's flowing into the left side of the box and subtract the energy that flows out of the right side of the box. And then I'm going to multiply by the area of the face of the box perpendicular and multiply by the time interval that I'm talking about. And then if I'm taking flux times area times time interval, I get the actual amount of energy that has remained in the box, right? Due to this flow in the x direction. And I can approximate this difference by this partial derivative. And so I can write the amount of energy that has, the net amount of energy that has flowed into the box due to this motion is going to be equal to that expression at the end here. Does that make sense? And you do the same thing for the y and z directions. So the net energy change inside the box due to the flow is just the sum of those things. And then you say, well, that's got to be equal to the amount of energy per unit time change inside the box, which is going to be equal to that expression. And so if energy is conserved. So if energy is conserved, the amount of energy that's left over in the box has got to show up in the energy density of the box. And then, so you can write that as this expression in your locally inertial frame. And if you divide through by all these differentials, then that's the same as that expression. So does that make sense? Okay, so the point is, this expression in the locally inertial frame gives you it tells you that energy is conserved. Energy and the other components, so I did this for the time component is about energy conservation. The other components are about momentum conservation in the x, y, and z directions. So this is about conservation of energy and momentum. And I've written it this way in a locally inertial frame, but if that tensor equation is true in a locally inertial frame, then the equivalent tensor expression has got to be true in an arbitrary coordinate system and arbitrary reference frame. So this is the ultimate tensor expression of the idea of conservation of energy and momentum. All right? So we can let's think about fluid pressures for a second here. So and I keep forgetting to say this, so I'm using units throughout where I'm measuring time in units of meters. In other words, I'm setting c equal to 1. And so in those units, if you think about it, pressure has units of force per unit area. And when we measure time and distance in meters, force per unit area is kilogram meters per, we would say, per second squared in normal units, but we're measuring time in meters, so it's kilogram meters per meter squared. And then unit area is meters squared. That's kilograms per meter cubed. That's the same units as energy density or mass density. They're all the same. So energy in this unit system is measured in kilograms. A kilogram of energy is a sort of an atomic bomb's worth of energy. And so what random speeds would particles in a fluid need to have if the fluid pressure is even 1% of the fluid density, energy density? Well, what we're talking about is that pressure term is going to be, the pressure is going to be equal to the fluid density times the average squared x velocity. Yeah, so you need that average. If you're going to get this to be 1% of rho O, then what does the average Vx have to be? Yeah, 1/10 of the speed of light. Okay? Is that going to be a common occurrence in most materials that we're aware of? No. You're not even going to be close to that. In fact, if you grind through the numbers here, which I invite you to do at some point, you'll find that your temperature would have to be about 50 million Kelvin before this quantity is even 1% of that energy density. So in most circumstances, we can neglect the pressure. It's just not that big a deal unless we're really talking about strongly relativistic fluids. All right, so that's mainly the point of that. All right, so that's one side of the Einstein equation. Let's talk about the other side, which has got to talk something about curved space-time. But how do we even decide what's a curved space-time? Look at those two metrics. Which one is a curved space-time? Which one is a flat space-time? Well, we know this because we've been working on examples. But just look at these metrics fresh. You got any idea? So this one is what? Yeah, that's flat space-time. That's the PQ coordinate system we were talking about. This one is, yeah, that's curved space-time because that's the metric of a surface of a sphere. So how would we decide? How do you know which one is which? We only know because we've been working with these before. So what we'd really like is to find a tensor quantity that somehow identifies a curved spacetime from an intrinsically flat spacetime. Now there are a couple of different ways to do this, and logically I think the nicest way to do it is to actually talk about geodesic deviation and look at neighboring geodesics and seeing whether parallel geodesics remain parallel, because that's really intrinsically, conceptually, the way to distinguish a curved spacetime from a non-curved spacetime. But mathematically, that's a really hard path, and if you're really interested in that path, take a look at my textbook, which goes over that in detail, and it takes 3 or 4 pages to work out all the math, and it's conceptually tricky and so on. But there is a faster way to get at it, and that's what I'm going to do with you today. A faster way is to look at the commutator of these tensor derivatives and think about it for a second. In a locally inertial frame, in a truly flat spacetime, I mean a completely flat spacetime, not just locally, but globally flat spacetime, these will reduce to ordinary partial derivatives. The order of ordinary partial derivatives doesn't matter, so this quantity will be 0, right? But if you think about what we're doing, if I have a general coordinate system in curved spacetime, then when I'm taking derivative, a tensor gradient of a tensor gradient, I'm going to be involved with taking derivatives of Christoffel symbols, right? And the Christoffel symbols involve first derivatives of the metric. So derivatives of Christoffel symbols are going to involve derivatives of the second derivative of the metric. And remember the flatness theorem that I showed last time? I can't set in a general curved spacetime, I cannot set all the second derivatives of the metric to be equal to 0. So since this will involve second derivatives of the metric, it might well indicate that this will be non-zero in a curved spacetime, where it's going to definitely be 0 in a globally flat spacetime. Yes? Yes, we can still go to in a locally inertial frame. Yeah, but you can't put to 0 the second derivatives. And so that's basically the issue. So this is going to expose those second derivatives. And those second derivatives really will be 0 in a globally flat spacetime, but they won't necessarily be 0 in a curved spacetime. So this is a candidate. This is clearly a tensor quantity, and it's a candidate then for a tensor that might indicate the difference between curved spacetime and flat spacetime. So here we're going to work it out. So here's one term in that expression. So I'm taking the tensor gradient of the tensor gradient of a 4-vector. And so you see what I did here. I expanded out this tensor gradient. So I've got to take the ordinary partial derivative and then a Christoffel symbol for the beta and a Christoffel symbol for the nu, and then I'm going to expand out the inside here, and I get a whole bunch of terms, and I'm not going to go through that step by step, but you can. It's just a matter of tracking it through. And then doing the same thing with the mu and nu reverse, that's easy. You just rename the indices, and then you write it down what the difference is, and then so here's the whole thing for this line, and here's the same thing with the mu and nu reversed, and you get a bunch of terms. But I want to point out, though, that you are involving the first derivatives of the Christoffel symbols. So you really are pulling in second derivatives of the metric here. And so you get a bunch of quantities. And so, for example, when you get those, this term cancels with this term because the order of partial differentiation really doesn't matter. And this term cancels with this term. Can you see that those are the same? Wait a minute, don't I have a gamma here and a sigma here? Why don't I care? Yeah, it's a bound index. I can rename it to be anything I like, so I could rename them both the gammas to be sigmas, and then those terms cancel. And similarly, this term cancels with this term because the Christoffel symbols are symmetric. And this term cancels for this term for the same reason, etc. So you get a bunch of cancellation, but you do have an expression left over. And since this is a tensor quantity and this is a tensor quantity, this whole thing had better be a tensor quantity. And that tensor quantity is called the Riemann tensor. Okay, and there is an actual, I mean, this is a pretty horrible tensor quantity. How many components does it have? 4 times 4 times 4 times 4, which is, yeah, 256 components. Yeah, sort of, right. So that, and it looks like it's all those Greek letters. Yeah. So, but there actually is an easy way to remember this. So, like say, if you're on a desert island and you need the Riemann tensor, you can remember it. Look at the third and fourth index. So this is the third and fourth index. In the positive term involving the derivative of the Christoffel symbol, 3 and 4 occur in that order. Here they're reversed. That's the negative term. Okay? So the mnemonic is 3 to 4 is positive. So the positive, so you got one derivative term of the Christoffel symbol, and then you've got a pair term that involves multiplying two Christoffel symbols together. And the pair, you have a sum over it, and you've got the 3 and 4, that's the positive term when the third and fourth index appear in that order. And you're summing over the inside thing. So the twins bond inside. All right? So 3 to 4 is positive. Twins bond inside. Now you can write down the Riemann tensor wherever you are. Okay? So there are symmetries to the Riemann tensor that are very important to get a hold of. This one is obvious because 3 to 4 is positive, 4 to 3 is negative. Both terms are, and so if you switch those last two indices, you get minus the same thing. And we can lower that first index by doing the normal lowering thing. And when you do that, you have other symmetries that emerge. If you switch the first two indices, you get a minus sign. If you switch the first two indices with the second two indices, just switch them like that, that's positive. If you add them where you're doing a cyclical rotation of the last three indices, so this, and here I've moved the mu to where the beta was, and the beta over and the mu over, and then I do the same thing again. They add up to 0. And then there is an important identity called the Bianchi identity, which is actually about the derivatives of the Riemann tensor. And here again, we're sort of rotating. Here the alpha and beta indices remain constant, but I'm rotating these three indices cyclically around. And these are all symmetries of the Riemann tensor. And you can derive these symmetries by going to a locally inertial frame, since you can evaluate a tensor quantity in any frame, and if you can show that it's zero in one frame, then it's zero in every frame, every coordinate system. So we can go to a locally inertial frame, and I'm going to write what this quantity is, and in a locally inertial frame, we know what the expression for the Christoffel symbols are. And here I've forgotten about the twin terms. Why do I forget about them in a locally inertial frame? Yeah, they are zero. Christoffel symbols at the origin of a locally inertial frame are zero. The derivatives might not be zero, but they are at zero themselves. So the twin terms go away. I'm just left with this. And I can write that out in detail. A couple of terms cancel. And you get this nice four-term expression for what the Riemann tensor is at the origin of a locally inertial frame. And here, there's another mnemonic, which is inner togetherness is positive. All right? And what I mean by that is here are the two inner indices of the Riemann tensor. And in the positive terms, in the two positive terms you have, those are together in either the derivatives or the metric indices. And in the negative terms, those two indices are split up. Okay? So splitting up those inner indices is negative. So now you can write this in any locally inertial frame. You can just write down what the values are. Okay? So for an example, a proof, say I want to show that switching the first two indices causes an overall minus sign. You just write it down and you reorder the indices, and it's a pretty easy proof. I won't go over it in detail, but I think you get the picture. And then, of course, if this is a tensor equation, which we've shown to be true in one coordinate system, but then it's automatically true in every coordinate system. And so going to the locally inertial frame can really save a lot of calculation work. Yes? Right. Yes, correct. Although the coordinate basis in a LIF, in a locally inertial frame, yeah, I could use an arbitrary, even then an arbitrary coordinate system. But no, I'm sorry. No, this is basically, the idea is that, and you can see this is involving second derivatives of the metric. If I were just concerned about the metric, it'd be the ordinary flat space metric. But I'm keeping it as G because the ordinary flat space metric has 0 second derivatives. But our coordinate system in our locally inertial frame doesn't necessarily have 0 second derivatives. And so I'm keeping it as G. But it's basically TXYZ coordinate system, same coordinate system you use in flat space. All right? Good. What else? Okay. So the importance of these symmetries is, among other things, we can count up how many independent components there are of the Riemann tensor. And because if I switch the first two indices or the last two indices, I get a flipping sign. Then if those two indices are the same, what does it mean about the value of the Riemann tensor? It's 0, because the only number that's negative itself is 0. Okay, so if I had this index the same as, well, this index the same as this index, so maybe both are R or something like that, it's got to be negative itself, which means it's 0. So a lot of terms are 0. So the only possibilities, and the order doesn't matter even if they're different, because I switch the order, I get the same thing with a minus sign. So those are not going to be independent. So the only truly independent components are going to be choices of the coordinates that are different like that. And I've got 6 choices, 0, 1, 0, 2, I'm just numbering the coordinates abstractly. 0, 3, 1, 2, 1, 3, 2, 3. Those are the only possibilities for non-zero independent. Okay? And then similarly for the AB, the alpha beta components. So here is a list then of all the possible components of the Riemann tensor that could be independent. Except I've got another symmetry, which is I can switch the first two with the last two, which means that all the components on the upper side of this diagonal are related to components on the lower side of the diagonal. They're in fact the same as. This submatrix is sort of is symmetric. Okay, so let's count them up. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay? But I've also got this relationship, which is usually trivially 0, and that shows you an example. The only non-trivial one, which actually says something, is that it says this plus this equals 0. And so one of these is not independent. So that leaves 20 independent components. Okay? Does that make sense? And does that number 20 ring a bell? That's how many non-zero second derivatives of the metric there might be. So what these represent is linear combinations of those second derivatives of the metric, 20 independent linear combinations of the 20 independent second derivatives of the metric that I can't set to 0. So this tensor is really going to represent the curvature of space-time by looking at those second derivatives that I can't set to 0. Okay, so we could actually have an exercise about this. So in two-dimensional space, there's only one Riemann tensor that's possibly independent, 0, 1, 0, 1. Why? What about 1, 0, 1, 0? That's going to be the same by symmetry. I flip both of those things. And so if I have 1, 0, 0, 1, that's flipping one of them. It's basically they're all going to boil down to this or be 0. And so in a two-dimensional space, all you have to do is evaluate what these things are. And it's actually pretty easy, though I'm not going to take the time for it now. I recommend doing this. Try and do it for our parabolic coordinate system. We know that that's a flat space, so it better be equal to 0, and it is, if you work it out. So in spite of so here you have a metric. You could work out what the Christoffel symbols are from the metric. We do that, and we've done that, and then you could use the Riemann tensor to test whether that metric represents a flat spacetime or a curved spacetime, and it'll come out flat, as it must. So I do recommend doing the exercise. So, but let's go on, and now we're going to actually try and, yes, question. That is correct. So what the Riemann tensor is, yeah, it's 0 if your space-time behind the coordinate system is flat. So the Riemann tensor is not necessarily 0, but it does, if it is 0, then it's indicating that the space-time behind whatever metric you're looking at is a flat space-time. If it's, and I should say 0 globally. That's right. No, that's the point. Yeah, that is the point. So say I have a truly flat space-time. I can choose any coordinate system I want for the flat space-time, like the one I did, this horrible parabolic coordinate. If I evaluate the Riemann tensor in those horrible coordinates, then it will become 0, and it'll be 0 everywhere. And that's the indication that the space-time behind the coordinate system is truly flat. And if it's not 0 everywhere, then it shows that at least at some points in your space-time, it's curved. And that's the beauty, that's the power of the Riemann tensor, is it gives you a coordinate system independent measure of whether the space-time is curved or not. That's cool. That's very nice. Otherwise, we'd be in pretty difficult position. So we're going to try and construct the Einstein equation now. We're looking for an equation of this form. We know that we've got to have this side. This is just a constant of some kind. And I'm going to, and we know that because this is a symmetric tensor, the way we've constructed it, then this has got to be a symmetric tensor, this Einstein tensor. And also because this has 0, this side has 0 tensor divergence, this had better have 0 tensor divergence. And so we're looking for a way of constructing this out of the Riemann tensor that has these two characteristics so that the two sides are consistent with each other. Does that make sense? So one candidate is the Ricci tensor, which we've already seen in a couple of contexts. But the Ricci tensor is a contraction along the first and third indexes of the Riemann tensor. And you can check, so I can put it with upper indices by simply raising various indices. And you can check that it is in fact symmetric. And it's just a matter of keeping track of all sorts of horrible indices there. And so the question is, does it have 0 divergence? And the way to do that is to evaluate it in a locally inertial frame. And so I put in what the expression for the Riemann tensor is in a locally inertial frame, and I do all the raising of the indices, and I can pull the derivative past all these, because the first derivatives are all 0 of the metric in the locally inertial frame. So I can simply bring the partial derivative in, and I get that, and a couple of terms do cancel, but I'm still left with 2 terms left over, and I can't rename indices in a way that makes those 2 terms equivalent. So it's not generally equal to 0. So it would be really nice if this tensor that we were looking for were the Ricci tensor, but it can't be. So now what do we do? Well, what else might it contain? This is a metric tensor in sort of upstairs form. And also, here is another symmetric tensor that I can construct where this is the curvature scalar, which is the trace of the Ricci tensor. And related to the Riemann tensor via that expression. And so what I'm going to do is I'm going to try and construct something out of these three terms where the divergence really is 0. And then I'll be good. Okay? So now the tensor gradient of the metric is automatically 0. Why? If I go to a locally inertial frame, the tensor gradient becomes just the ordinary gradient. And why is that 0 in a locally inertial frame? Yeah, basically because the metric tensor is a Minkowski tensor through the first derivatives. Okay, so basically it's because the first derivatives of the metric are automatically 0 in a locally inertial frame. Okay, and so so this term is fine. I don't need to worry about that. It's going to be the divergence of that is going to be automatically 0. So I'm worrying about this term. I want to know what that b has got to be. And the way to do it is through the Bianchi identity, which tells you, which originally is in this form. And so here what I'm doing is multiplying by a bunch of metric terms. I multiply each term by the same combination of metric to raise the indices. And if you work through the Bianchi identity, what it becomes, this term becomes just the curvature scalar. You can see that I'm summing over beta and nu, and I'm summing over alpha and mu. And so this term just becomes the curvature scalar, and I've got this factor left over. These two other terms become two factors, if I rename indices, two factors of the Ricci tensor, and that's equal to 0. Now if I divide both sides by 1/2, then I can rewrite it this way. And so that's the form we're looking for. We know that that quantity is going to have 0 divergence, 0 tensor divergence, which is exactly what we need. And so our field equation is going to be of this form. In other words, we needed to choose that b factor to be -1/2, and then we can get a everything on this side then has 0 divergence. And so this is the Einstein equation. Now, in order to determine, an important side note, if I take the trace basically of both sides of the Einstein equation as we have it, then this just becomes R by definition. This becomes R times the trace of the identity matrix, which is 4. So 1/2 times 4 is 2. And I get another factor 4 there. And so I get this as sort of the trace of the Einstein equation as we have it. And then you can show that if I can basically subtract terms from both sides to put the Einstein equation in this form, where instead of having extra complexity on the curvature side, I put the extra complexity on the stress energy side, and that makes it easier to solve. And this is a very useful form of the Einstein equation. It's the same thing, but just rearranged in a way to put the complexity on the stress energy side. Okay, so there, and basically the exercise there asks you to show those things, and I'm going to leave that as something you can work on, but that's not difficult. So to determine K, I'm going to skip over a lot of this except to point out a couple of things. We're going to take a kind of a Newtonian limit to see what it should be, and I can mess around with the geodesic equation in the case. So if I want to get the acceleration of a particle that's free in this limit where I'm just tweaking the metric a little bit away from flat space-time, so a weak field limit, and you can write, so here's the geodesic equation, but I've got a version of this double derivative with respect to tau. You could write it as a double derivative with respect to ordinary time by pulling out a couple of factors of the time component of the for velocity of the particle, and for a particle at rest, or that's moving, well, I'm sorry, at rest is not required. The particle can be moving, that's fine. Oh, no, it is required because I'm omitting a bunch of terms involving ux and uy and uz, but if the particle's at rest, those are all zero. And so the acceleration of the particle is simply this particular component of the Christoffel symbols. And so in Newtonian physics, we would say acceleration is minus the gradient of the potential. And so I'm going to sort of identify those two things. This is the GR equivalent of the gradient of the potential. All right? And hold that in your mind for later. And then you look at the Einstein equation and you expand it out to the same order. And I'm not going to go through the details here, but it turns out that the Ricci tensor, or time-time component, corresponds to the left-hand side of what we want. And so if you look at that, then you can decide, since we know what that constant was in the case of the Newtonian limit, we can figure out what the constant has got to be in terms of general relativity in the Einstein equation, and it's got to be that 8 pi times g. And I'm deliberately not setting g equal to 1 in my coordinate system because I want to see that correspondence. So if you go over the text, you'll see the details of how this works out, and it's very helpful. So we do have this, I'm sorry, even in the Newtonian limit, we have this lambda factor coming out. It's sort of adding. This is an element that doesn't appear in Newtonian mechanics, and so it better be small compared to the density of matter and energy for Newtonian sources of gravity. But that's all we can say about it. And nowadays, people can take that lambda term to be the vacuum energy or dark energy term. And so rather than putting it on the left side of the Einstein equation, we nowadays put it on the right side of the Einstein equation and consider it to be a vacuum energy stress energy tensor, which is equal to that. And so the Einstein equation can be written as G mu nu is going to be defined to be just this part without the vacuum energy term. And then we move the lambda term over to the other side to be a stress energy of the vacuum, basically. And so here is the full Einstein equation as we now have it. We've determined that this is 8 pi g by comparing with the Newtonian limit, and this is by definition the Einstein tensor, And then this is the stress energy of everything, including the vacuum. Or equivalently, I can isolate this term by doing the trick I was showing before and put the complexity on this side. And it's a useful exercise to show that for the vacuum, this term is just plus times the lambda times the metric over 8 pi g. Yes, question? Yeah. Yes. Yeah. Absolutely. Yep. Yeah. Yep. 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 Yeah. That's right. That's right. That's absolutely right. This is a choice that people have made. And Einstein, when he originally developed that cosmological constant term, did not make that choice. He thought that it was a part of the left-hand side of the Einstein equation, and developed it there. And in fact, we talked a little bit about how Einstein wanted to make a stable solution for the universe because at the time that he was writing in the teens, 19, 16, 17, 18, people didn't know that the universe was expanding. It was static universe model was the standard model. So he put in this constant term to make the universe static. Otherwise, you've got dynamic solutions. And he didn't want that. So he put in this term. It's allowed, obviously, by the logic that he developed the equations. But it turns out that if you put in that term, yeah, the universe can be static, but it's unstable. So it's not going to stay static. And he realized that after a while, and then came the publication of Hubble and others that showed that the universe really was expanding. And Einstein famously retracted this term and said it was the worst mistake he ever made in his life, right? But the truth is, it's back. And it's back because we discovered the universe expansion is actually accelerating. And this is the nice way to explain that. But as the point you were raising, we really don't know for sure that the expansion is caused by a term like this. Could be. It would do the trick. It does what you need as long as lambda has the right value. And so all those models that you see from the based on the microwave background of how the universe is constructed, and this much dark energy and this much dark matter and so on, they're all based on this assumption that this is the way the dark energy is. Now maybe lambda is truly zero, but there's some other kind of dark energy. And so what people are trying to do is actually see whether the vacuum energy, by looking at details, see whether the vacuum energy actually has this form. And the jury is still out on that. It looks pretty good as far as I know at the present, but these are details that are yet to be determined. So there is some issue here. And when I began teaching general relativity, I taught that lambda is equal to 0 because a first prediction from lambda from particle physics says, yeah, you could have a lambda due to ground state energies of the vacuum, but it would be 120 orders of magnitude larger than it's measured to be. So that's a pretty large discrepancy. And so I taught my students that the only way to really explain that is that there must be some kind of perfect cancellation that cancels everything out. And so lambda is equal to 0. But how to explain that it's not 0, but you cancel 120 orders of magnitude worth of lambda and just left with a little bit left? I don't know how to do that. And no theorist knows how to do that yet. And people are trying to fill in the gaps experimentally. So this is a really interesting part of, and it's got an interesting history in gravitational theory. But this is the way that people do it nowadays. But you're totally right that there are lots of questions raised by that. Yeah, that's the thing. Yes, it does work well, and it seems that as far there is no way to contradict that with evidence that we have at present. Yes, yes. So more detailed experimental work will help nail this down. But I do want to spend some time on an issue here, so the way I've presented the quote-unquote derivation of Einstein equation was basically the way Einstein himself did it. He said, oh, I know the stress energy tensor is divergence is 0. I know it's symmetric. How can I make a curvature side, an Einstein tensor that satisfies those conditions? And this does it. But this, if you think about it, this represents 10 second-order coupled nonlinear differential equations in the 10 unknown metric components. And in principle, you ought to be able to solve for the metric, right? 10 equations, 10 unknowns, no problem. Well, the issue is we shouldn't be able to solve for all 10 components of the metric, because that would mean not only determining the curvature of space-time, but determining the coordinate system. And the whole point of general relativity is it's independent of coordinate system. You can choose any coordinate system you like. So we should not be able to determine the coordinate system. But we don't have the ability to determine the coordinate system, because this equation automatically solves for equations of constraint because of this. Okay? And so I've really only got 6 independent equations. There are 4 equations that this solves automatically. 4 equations of constraint that just the construction of the metric tensor means that there are these 4 internal equations of constraint. So I only have 6 equations left over, which gives me 4 degrees of freedom to choose coordinates. Okay, at least we're not getting a contradiction. But what this really opens up is a really interesting different angle on how you can think about this relationship. You can say, forget about conservation of energy and momentum. I've got to have this or something like that. I've got to have 4 internal equations of constraint so that I can't solve for the coordinate system. And so this is really required by the principle that coordinates really are your choice. So you could take that as a symmetry. This allows us the freedom. This is a way of expressing our freedom to choose coordinates. This is required just because we need that coordinate freedom. But if this is true, then this is true. And so our symmetry of being able to choose coordinate systems arbitrarily, the equations work in all coordinate systems, means that energy and momentum is conserved. Yes. Yeah. Yes. So this is, it turns out that if you really do the mathematical background of this, if you choose the Einstein tensor, and I thought let me see if I have a slide on this. No, I don't. If you choose the Einstein tensor uh, to be linear in the Riemann tensor and zero in flat space, so you're choosing the Einstein tensor to do that, then the only, you can construct, the Einstein tensor can really only be of this form with this arbitrary, yeah. Uh-huh. Yeah. No, is what I was getting to that, and the answer is no. But there are some other constraints that you sort of put on it. Linear in the Riemann tensor, things like that. So you could construct nonlinear equations that might be more complicated, that might have. But this is the only kind of constraint that you can put on. It's available from the Bianchi identity. Otherwise, there are no other internal constraints that you could put on the theory in an obvious way. So, so the point is that a modern perspective on this is that we take our symmetry. How many of you know about Noether's theorem? Yeah. All right. Noether's theorem basically says if you have a symmetry in your equations of physics, you will have conserved quantities. Our symmetry in this case is that the laws of physics are the same in all coordinate systems. Our conserved quantities as a result of that, this is an expression then of Noether's theorem. Our conserved quantities as a result of that are energy, momentum locally. Okay? And that's the modern way to look at it. Rather than taking this as a priori true and deriving this, we take this as true to be giving our ability to choose coordinate systems arbitrarily. The fields are fundamental and they impose conditions on the matter to conserve energy and momentum. It's an expression in Noether's theorem. All right? Yeah. Yes, the T's are conserved. Yeah. Yeah. Uh-huh. Yes. Yeah. Well, I'm gonna talk of it. Yeah. So you're basically saying yes. It looks like this means that that we've got a time translation symmetry and a space translation symmetry. It's a little bit more complicated than that, which is what I'm going to get to in a second. But because expresses local conservation of energy and momentum, and it's just conservation of energy and momentum as associated with matter. Okay? And it's not a global conservation law. It simply says that when you go to a locally inertial frame and you're just looking at matter and energy, everything's conserved. Uh, And so that raises a really interesting question, and I think I'm going to skip ahead to that. Oh, I just want to say, if you look in the handout, in the printed version of my talk, you'll see a fact that the local energy conservation equation implies the geodesic equation, that matter will follow the geodesic equation. Okay, so you don't even need the geodesic equation as a basic hypothesis of the theory. It falls out of the theory. So all you need truly, besides a bunch of subsidiary conditions on the mathematics, the conceptual root of general relativity is coordinate systems don't matter. And everything else follows from that. So that's a kind of a cool result. Okay, so does the gravitational field then have energy? So before I was saying that the acceleration corresponded to this Christoffel symbol for a particle at rest. And so if I were doing a sort of electromagnetic thing, this would be like the electric field vector. Okay, and so I should have maybe a gravitational field energy density that's proportional to that field vector squared. That's sort of the normal thing that we do. But what's the problem with that? Well, in a locally inertial frame, all the Christoffel symbols go away. So what's the energy density of the gravitational field? Looks like it's 0. All right. So there is another problem with trying to assign an energy to the gravitational field. In flat space-time, as long as you have a globally flat space-time, you can take this this divergence and use the divergence theorem to integrate over a volume and say energy that's flowing into that volume has got to equal energy flowing out of that volume, and so derive a global conservation of energy law, right? But we can't do that in a general curved space-time. You can't do that integral. The divergence theorem doesn't work that way. It's for ordinary partial derivatives, not for this tensor derivative. And so you can't do that integral, which means you can't come up with a global conservation law in general relativity. And if you think about it, this is a consequence of Noether's theorem as well. Noether's theorem says that because the laws of physics are independent of time, energy is conserved. And because they're independent of position, momentum is conserved, exactly what you were talking about. But what happens when time and position are intrinsically part of the equations that you're working with, the laws of physics that you're talking about? Then do we really have independence of time and independence of position? It's hard to even talk about what that means. And so is this equation independent of time? It involves time. So what does it mean to say that? So it turns out that this is actually a very contentious issue in general relativity. And a colleague of mine remembered going to Caltech and sitting in a seminar room where people got into a heated argument about whether you can talk about energy conservation in general relativity or not. And there are various people who say various different things about that. And it is true that, for example, in the Schwarzschild metric, if you take the Schwarzschild metric, it's symmetric in time, as we were talking about yesterday. It's also symmetric in rotation. And because of those things, you have conserved quantities, and which correspond to energy and angular momentum. And the orbits will then conserve energy and angular momentum, and the equations look almost exactly like, with one additional term, the Newtonian equations. And that actually I showed in the appendix of yesterday's talk. You can see that. So yeah, you can have energy conservation that looks like Newtonian conservation that emerges from real symmetries of your physical situation. But the bare law itself doesn't have that symmetry, and so you really can't say. And this particularly arises in the context of the universe. Is energy conserved in the universe as a whole? Open question. And probably not, because the universe is different now than it was a long time ago. You don't have that time translation symmetry, unlike a black hole, which once it's settled down looks the same now as it did before. So the physical situation is not time symmetric. You don't have necessarily conservation of energy. So this gets to be a real tough problem when you talk about gravitational waves. Because if the gravitational field doesn't have energy, then can a gravitational wave carry energy? What does it mean for a gravitational wave to carry energy? And this is a difficult problem. And I'm going to show you in the last lecture of my series a solution to that problem that kind of works. And so that we can talk about it in the ways that we usually talk about energy conservation and say, yes, the orbital energy of this binary pulsar system is really decreasing an exact amount of the gravitational waves that are emitted. And there's a way to do that mathematically that all makes sense. But it's basically, so there are cases where this idea works, where the conservation of energy and momentum really work. When the metric has symmetries, like the Schwarzschild metric, then you can talk about energy conservation and angular momentum conservation. Or when you have a region of curved space-time that's entirely surrounded by flat space-time, then what you can do is integrate this over the region large enough that you're in flat space-time, and then the divergence theorem works, and you can say, okay, the energy that's coming through my surface has got to be equal to an energy decrease somewhere within that curved space-time region. I don't know where. I don't know where that energy is, but the total amount of it is related to what's coming across the surface. And that's the trick that we're going to use essentially with gravitational waves. We're going to get a way for it to work. Okay? So, hey, I actually got done. What an amazing thing. So we actually have a few moments for questions. So, yeah. Yeah. Yes, right, exactly. That's correct. Exactly. That's right. Uh-huh. Yes, it is an open question. It's an important theoretical question. So what he's saying is that this, if I can rephrase the statement, and also for the record, that the issue is that in general relativity, you have no a priori background uh, that you can use as a reference to talk about energy conservation or momentum conservation. The geometry of space-time is determined by the equations themselves, and therefore, in a certain sense, the details of the laws of physics are determined by the equations themselves, so you don't have these sort of background symmetries that would allow you to talk about, in a Noetherian way, talk about energy conservation or momentum conservation. If you did have an a priori background, if instead of a gravitational field representing the core geometry of space-time, it was a tensor field just sitting on top of flat space-time, and people have worked out such gravitational theories, then you could talk, because you would be able to go back to the flat space-time, you could talk about what is conserved and what's not conserved in that kind of context. And so one of the deep principles of general relativity that it's founded on is no a priori geometry. The geometry is determined by the equations themselves and nothing else. And that's what leads to this problem. But yeah, he was pointing out that when we do gravitational wave physics, we do basically consider ourselves to be in flat space, and the metric perturbation, the little tweaking that we do of the metric, we treat as if it were a tensor field on top of the flat space-time. And that's the weak field limit of general relativity. And in that weak field limit, we can talk about energy conservation and so on. What we can't do is in the strong field limit. And so we can say, coalescing binary star emitted this much mass in terms of gravitational waves, and that mass has gone from the highly curved region, but we can't tell exactly where that mass energy was located, particularly as the thing is spiraling in, because you're in the strong field limit. Okay? Any other questions about this? Yes, there have been lots of attempts. So the question was whether people have tried to get useful ways of describing the energy in a gravitational field. And this is part of why this is contentious, is that some people have devised schemes for doing this, but the tensor quantities that they come up with are funny tensors. They're not really independent of coordinate systems, or in order to be independent of the coordinate system, you have to integrate over a certain region of space. What's pretty clearly established is that you cannot define a tensor that talks about the energy density of a gravitational field at a point. Yeah, at all. Everything would go to zero. Yes. Yes. Yep. Absolutely. And the reason that we can talk about it that way is because of the Penrose process. So, yeah, I'm sorry for everybody to hear. He's talking about, we know that the Penrose process can extract energy from a rotating black hole. You can drop garbage in the yeah, right. But the whole issue is that that's my case here. When you've got a curved region of space-time surrounded, yeah, when you've got a curved region of space-time surrounded by a flat region of space-time, then you really can talk about it. And the Penrose process really is a valid physical process, and it really does extract energy in this sense. Yeah, because we're surrounding that rotating black hole with a asymptotically flat space-time. And so, yeah. And then what you're doing, in a certain sense, is you're extracting the energy from the space-time somewhere, And the so at infinity you say, oh yeah, my mass of my black hole is actually decreasing because I've extracted energy from it. But you can't say where that energy is coming from. It's just coming from somewhere down there. All right? Other questions? Okay. Yeah, that's right. I will speak in a future session, in the last session, about a way of characterizing the energy. I don't think it's exactly the Weil tensor, but it's a way of characterizing the energy, and we will indeed talk about that. Okay, great. Thank you, everybody, for your attention. Yeah.